Good evening. I think we can class the start for today. So today is the week 6 of the live interactive session for the NPTEL course, an introduction to climate dynamics, variability and monitoring. Today I thought we'll solve a couple of assignment questions and discuss the concepts related to that so that you'll get a revision kind of thing. This was one of your assignment questions, I think in week 2. So the question was, which of the following atmospheric temperature profile diagrams best represents the conditions that would lead to the strapping plume behavior? In these diagrams, the solid line represents the atmospheric lapse rate and the dashed line represents the adiabatic lapse rate. So we discussed the different lapse rate and the so we discussed the different lapse rate and the different stability condition. The last, yeah, yeah, I'll explain that actually. I'll be explaining it actually. Yeah, just give me a second. I'm just trying to figure out how can I get the point. I'll just open the slides and PowerPoint so that I'll be able to write. Yes. My screen is visible, right? Oh, fine. So yeah. So last class we were discussing about the different lapse rate and the different stability parameters. Just to revise, we know there is something known as the environmental lapse rate, which basically gives you how the temperature is changing in the atmosphere, like the tropospheric lapse rate that we learned, the value is around 6.5 degrees Celsius per kilometer. So this is what is known as environmental lapse rate. And then we learned something known as the dry adiabatic lapse rate, which is given by G by Cp, which is having a value of around 9.8 degrees Celsius per kilometer. So this is in case of a unsaturated dry air. In case of an unsaturated dry air parcel, if it is vertically moving in the atmosphere, what will be the rate at which the temperature decreases? So that's what dry adiabatic lapse rate gives. And then we learned about another lapse rate known as the saturated having the value of saturated adiabatic lactate will always be less than dry adiabatic lactate, because in case of saturated adiabatic lactate, since it is moist air parcel, once the moist air parcel becomes saturated, and then again it keeps on moving upwards. Once it gets saturated, again when it is moving upward in the atmosphere, it will again cool down and condensation will start to begin in the parcel. If a saturated air parcel is forced is again moving up in the atmosphere, then condensation starts to begin, and there will be release of latent heat of condensation, which will act as a heat source, which will warm the parcel. So the saturated adiabatic lapse rate, which is the rate at which the temperature of a saturated air parcel decreases when it is going vertically in the height, is less than the rate at which the temperature decreases in a dry air parcel. So due to condensation and supply of latent heat of condensation, the saturated adiabatic lapse rate will always be less than the dry adiabatic lapse rate. And then we learned about three different stability conditions. First one was stable atmosphere. In case of a stable atmosphere, the value of environmental lapse rate was less than saturated adiabatic lapse rate and dry adiabatic lapse rate, which means in the atmosphere the temperature is having a lower rate of decrease compared to that of the dry and moist air parcel. And the second one was in case of an unstable atmosphere. In case of an unstable atmosphere, we learned that the saturated adiabatic lapse rate and dry adiabatic lapse rate will be having a lower value compared to that of the environmental lapse rate, which means the temperature of the environment or the atmosphere will be decreasing at a higher rate compared to that of the parcel, so that the parcel will always remain warmer than the atmosphere or than the environment. And the third one we learned was conditionally unstable atmosphere. Conditionally unstable. In this case, what happens is that the value of environmental lapse rate will be between that of saturated adiabatic lapse rate and dry adiabatic lapse rate, which means the value of environmental lapse rate will be greater than that of saturated adiabatic lapse rate and less than that of dry adiabatic lapse rate, which means that initially when the parcel is unsaturated, the parcel will be stable, whereas once it gets saturated, then the parcel will become unstable. So that was the third stability, which is conditionally unstable atmosphere. And we also, in terms of change in potential temperature and in terms of change in equivalent potential temperature, we again defined condition. And in case of stable atmosphere, the condition was that the change of potential temperature with respect to height will be greater than 0. Similarly, the rate of change of equivalent potential temperature with respect to height will also be greater than 0. Whereas in case of unstable atmosphere, the values will be less than 0. The change in potential temperature with respect to height will be less than 0 in case of unstable atmosphere, and in case of conditionally unstable atmosphere, the change of potential temperature with respect to height, which is d theta by dz, will be greater than 0, whereas d theta e by dz, which is the change of equivalent potential temperature with respect to height, will be less than 0. So these are the things that we learned in the last class. So here we have different stability conditions. So the different options basically shows you different stability conditions. Atmospheric profile corresponding to different stability conditions. You have something to ask, Vishwajit? Yeah, tell me. Mm. So yeah, it's the same actually. So when the parcel is unsaturated, it is stable, and when it becomes saturated, it becomes unstable. So it's the same thing. We can say it in both ways, either conditionally stable or conditionally unstable. Yeah. Yeah. So that has a three different conditions. So here in this question, we have been given different temperature profiles with different environmental lapse rate and adiabatic lapse rate values. From these atmospheric profiles, we need to identify which all is stable and which all is unstable, and what are the plume behaviors corresponding to different stability conditions. So here in this question, it is given that the solid line represents the environmental lapse rate and the dashed line represents the adiabatic lapse rate. So before solving this question, we will have a look at different plume behaviors. So there are basically six different plume behaviors based on the stability conditions of the atmosphere. So the first one is looping. So here the dashed line represents the adiabatic lapse rate and the solid line represents the environmental lapse rate. So from this, we can see that the slope of the environmental lapse rate, which is the solid line, or the environmental lapse rate value is actually less than the dry adiabatic. Sorry, the environmental lapse rate value is greater than the dry adiabatic lapse rate. The environmental lapse rate is greater than the dry adiabatic lapse rate. The solid line is having a higher slope compared to that of the dashed line. So in this case, environmental lapse rate is greater than the dry adiabatic lapse rate. So can you tell me if the atmosphere is stable or unstable? If the environment, yeah. So if the environmental lapse rate is greater than the dry adiabatic lapse rate, is the atmosphere stable or unstable? Yeah. So this basically represents an unstable condition of the atmosphere. So in an unstable condition, how will the plume behave? So the emission from a chimney or the plume that is coming out of a tower of a factory or something will basically have a looping behavior, which means it is free to, since the atmosphere is unstable, the plume is free to move both upwards and downwards. So because of that, it will basically form a looping behavior. It will have a both vertically upward and downward motion. So basically, it will attain a looping behavior with very high dispersion. The dispersion will be very high. So in the presence of an unstable atmosphere, the plume will have a looping condition, which means it is free to, since it is unstable, it is free to move both vertically upward as well as downward. So basically, it will attain a wave-like dispersion. So in this case, there will be high dispersion of the pollutant. So that is the first condition, which is looping. So in the presence of an unstable atmosphere, the plume will basically have a looping behavior. Okay. Now the second one. Second one is the yeah. So the second one is when the environmental lapse rate is equal to the adiabatic lapse rate, which means the atmosphere is neutral. Yeah. So second one is when the environmental lapse rate is equal to the adiabatic lapse rate. Both the environment and the particle are having the same lapse rate values. So both, so it is not, the atmosphere is neutral. It's neither unstable nor, so what happens is that the pollutants that are being emitted from the tower will have a coning shape. So it will, like, based on the wind speed or wind direction, it will basically move according to the wind. So basically it will attain a coning shape, such as like both sides it will kind of get dispersed. So it will be like a coning shape. That is the second one, is coning plume behavior. And the environmental lapse rate is equal to the adiabatic lapse rate, and when the atmosphere is neutral. That is So that is neutral. Now the third condition, third is basically known as fanning. So in this condition, what is happening is that your environmental lab state is actually having a positive value. So we know that in the atmosphere, the general tendency of the temperature profile is to decrease with respect to height, right? In the troposphere, we have a negative lab state value. When we plot the temperature profile in the troposphere, if this is the surface, this is the typical profile. As we go up in the atmosphere, the temperature should decrease. But during certain conditions, during certain periods, the an inversion layer is actually observed in the atmosphere, which means instead of decreasing the temperature with respect to height, the atmospheric temperature will have an inversion profile, which means the temperature will be increasing with respect to height, which basically represents a highly stable condition. If the atmospheric temperature is increasing with respect to height, it restricts the vertical motion of particles. There will be zero vertical motion of the particle. So atmosphere is highly stable. In this condition, when there is an inversion layer in the atmosphere, what happens is that the plume will be highly restricted to either move upward or either move downward. So it will just move in a thin line. So as you can see, it won't move upward or it won't move backward. It will just move in a small channel kind of structure. So this is the third one, which is known as fanning. So during fanning or uh, fanning plume behavior generally happens when there is a surface inversion layer present. Inversion layer means the environmental lab state is having a positive value. Or when you look at the vertical profile of temperature with respect to height, the temperature will be increasing with respect to height. This basically represents a highly stable condition and during which the movement of the plume is highly restricted. So what happens is that it will move in the wind direction. Based on the wind direction, it will move in a small channel instead of dispersing vertically upward or down. So that is the third one, fanning. It is highly stable. The atmosphere is highly stable. Yeah, V. Okay, that basically represents the wind speed actually. So the plume behavior also depends on the wind speed. Like if it is high, low, moderate, and all those things as well. So that's what it represents. So as we go up in the atmosphere, so you can see the arrow size is increasing as we go up in the atmosphere. So this is because of the lower roughness length. So as we go up, there is less restrictions for the wind to blow. So because of that, as we go up in the atmosphere, the wind speed will keep on increasing. So because that's why we have like the increasing arrow sizes with respect to height. So V just represents the wind speed. So this the plume behavior, yeah, yeah. Along with the stability conditions is also dependent on the wind speed. So what is the wind speed also? That also determines the plume behavior. So that is the third one, which is fanning. Now the fourth one is fumigation. In case of fumigation, what happens is that we have, so now you understood what is inversion layer, right? Inversion layer is when there is an increase in temperature with respect to height. So then in case of fumigation, what happens is that we have an inversion layer on top of the stack. Stack height is basically the height of the source of the plume. So this is what is basically emitting the pollutant. So this height is basically known as the stack height. The source of the plume is known as stack. So this is stack height. So if we have an inversion layer above the stack height, what happens is that the dispersion of the pollutants above the stack height is highly restricted. Because it is highly stable above the stack height, the pollutants cannot move above it can't move, go up. So what happens? And whereas below the stack height, the atmosphere is either neutral or unstable. So we have inversion condition in case of fumigation. We have inversion above stack height and we have neutral or unstable conditions. Neutral or unstable condition below stack height. So in this case, what happens is that the dispersion of pollutants in the upward direction is highly restricted. So it can only move downward. So in this case, the pollutants will disperse to the downward direction, which means where all of us live, like where there is high, all living beings are actually. So this condition is very much dangerous. So when like during night time and all, this kind of condition happens, and this is very dangerous to all the living beings because the dispersion of instead of going up in the atmosphere, the dispersion is actually happening near to the ground. So this is very much dangerous to all the living things. Along with human beings, all the animals, plants, and everything will be affected if the pollutants are dispersing more towards the ground rather than going upwards. So fumigation is very much dangerous. It is a very dangerous condition, and the plume is actually getting dispersed to the ground. So that is the fourth one, where there is inversion above stack height and neutral or unstable condition below the stack height. So in this case, since the plume motion is restricted above the stack height, it will disperse towards the ground only. So because of that, there will be high pollution near to the ground. So that is fourth one, fumigation. Now the fifth one is lofting. Lofting is that it is similar to fumigation, but in this case, the inversion layer is below the stack height. So here, the inversion is below stack height. Instead of above, the inversion layer is present below the stack height. And again, neutral or unstable condition above stack height. So in case of lofting, we have inversion layer below stack height and unstable condition above stack height. And unstable condition above stack height. In this case, the motion of the plume towards the ground is highly restricted. So the plume will get dispersed in the upward direction. So this is a very safer condition for us because the dispersion towards the ground is very less, or it is highly restricted. So this is lofting. Now the fourth one, like last one, is basically trapping. In this case, we have two inversion layers. So fumigation and lofting is basically combined. So in this case, we have an inversion layer above the stack height and with near to the ground also another inversion layer is present. So I hope you are able to see the inversion layers in the figure. So this black line, when it is having a positive slope, then that is basically another inversion layer. So you can identify inversion layer if the temperature is increasing with respect to height. So here we have two inversion layers. First one is this, which is near to the ground, and then the another inversion layer which is above the stack height. So in this case, what happens is that below and above stack we have inversion. Inversion near to the ground and above stack height. Yeah, in trapping there should be two inversions, and the dispersion occurs within that unstable layer only. So in between the stable above and stable below layer, there is a unstable layer in between. So the pollutants disperse within this layer only. So this is what happens in case of trapping. So this is the sixth one. So there is basically six different plume behaviors based on the stability conditions. I hope it is clear what are the different stability conditions and what are the different plume behaviors. Okay. Yeah. Okay. So now let's try to solve this question. So here it is written that basically which temperature profile is basically leading to trapping plume behavior. That is the question. So let's see which is matching the trapping behavior. So here the first one is basically having an inversion layer above the stack. Correct? If you see, this one is having an inversion layer above the stack. So this will be representing which behavior, can you say? If we have an inversion layer above the stack height. This will basically gives you what plume behavior? So here we saw when we have inversion layer above the stack, right? We basically have the plume behavior known as fumigation. So the dispersion will be mostly towards the ground, right? So this will basically result in what is known as fumigation. So in this question, we don't have the profile which exactly matches the trapping behavior, but this one is actually having an inversion layer near to the ground. Then we have unstable atmosphere, but for trapping, we should have an inversion layer on top also. But since this is mostly closed, yeah, yeah. So I think, yeah, both inversion layers are not present, but we have an inversion layer near to the ground. So this actually represents to the condition known as lofting, I guess. So in case of lofting, we have an inversion layer near to the ground. Then we have an unstable condition. So this exactly matches lofting. But here I think this is the profile which closely matches the trapping condition. So this is basically given as answer in your assignment thing. So this doesn't exactly matches, but this among the different options given, this is the one which closely matches the trapping plume behavior. So maybe that's why. Okay, what did you? Okay, you didn't. What did you give? Which one did you give as answer? C you give. Knowing the plume behavior. Yeah, yeah, yeah. I hope now it's clear. Okay, fine. So the third one will resemble to what? Third one is a neutral condition. Both ELR and DLR are parallel to each other. So in that case, if ELR is equal to DLR, it will basically result in con. So this is a parallel condition. Both are almost equal. So this will result in con. And finally, the last one. In this, the ELR is positive. This is a surface inversion condition. ELR is positive throughout the atmosphere. So in that case, it will result in fanning. Yeah. So this is fanning. Yeah. So yeah, that is all about the plume behavior. And this was one of the questions in your week 12 assignment. Now let's move forward. So yeah, which of the following conditions indicate a vertically unstable atmosphere for an unsaturated air person? So we need to find the condition for an unstable atmosphere. And DLR, which is gamma D, and environmental lab stage, which is gamma, is given. So in case of an unstable atmosphere, what will be the condition? Which will be having higher value? DLR or ELR? Yeah. Yes, exactly. So gamma D less than gamma will be in terms of lab state, and in terms of potential temperature, d theta by dz less than 0. This resembles the vertically unstable conditions. Now, the saturated adiabatic lab state is less than the dry adiabatic lab state primarily because, so just now I told you that the saturated adiabatic lab state value will always be less than the dry adiabatic lab state because there is an additional heating that is happening in the passage. So can you tell me which is the correct answer? Saturated air is denser than dry air. Condensation of water vapor releases. Yeah, B is the correct answer. Yeah. condensation happens in a saturated parcel, saturated air parcel, which basically acts as a heat source which keeps on warming the parcel. So because of that, the saturated adiabatic lapse rate will always be less than the dry adiabatic lapse rate. So this is in case of unsaturated conditions, and this is in case of saturated condition. So because of condensation, there is an additional heat source that is keeping on warming the saturated air parcel. So because of that, the saturated air adiabatic lapse rate will always be less than the dry adiabatic lapse rate. No questions for that? Okay, two more questions were there. I don't know, I think they did the slides or something, or it got misplaced. Okay. Yeah. So the next question is, just let me see. There were two more questions. I think I misplaced the questions. I will go to the site and then show you the questions also. Yeah, I'm just taking the assignment questions from the NPTEL site actually. So two more questions were there actually, so I think I misplaced it or something. Yeah. Yes. I'll just share you the screen. So in this, are you able to see the questions? Okay. So the eighth question. So dash is the temp. Oh, I think the answers are also there, but still it's fine. Uh, the temperature that a moisture puzzle would have if all its moisture were condensed out under adiabatic conditions and was adiabatically compressed or expanded to a reference temperature P0. So the options are virtual temperature, equivalent potential temperature, and potential temperature. So do you remember what was virtual temperature? Yeah, equivalent potential temperature is the correct answer. So I just revise what were the other things as well. So virtual temperature is a temperature that yeah. So virtual temperature is a temperature that a dry air parcel would attain if it had the same density as that of a moisture parcel. So in that case, the temperature attained by the dry air parcel is known as a virtual temperature. And virtual temperature will always be greater than the normal temperature. And potential temperature, we know that is the temperature that the air parcel would have if it is adiabatically expanded or compressed to a standard pressure level, which is generally taken as 1000 F. So that is potential temperature. And equivalent temperature is when all the water vapor that is present in a moist air parcel is condensed out under adiabatic conditions. So once you have condensed out all the moisture that is present in an atmosphere, you will get equivalent temperature. Now, if you bring that parcel to the standard pressure level P0, then it becomes equivalent potential temperature. So those are the three different potential temperatures that we learned in the previous class. And yeah, I just want you to solve this question as well. So an air parcel starts at a pressure 950 hectopascal and has a temperature of 22 degrees Celsius. So we have an air parcel with the initial pressure, which is 950 hectopascal, and the initial temperature is 22 degrees Celsius. It is lifted adiabatically. Now, the environmental temperature at 700 hectopascal is measured to be 0 degrees Celsius. Using R by Cp is equal to 0.286 and the reference pressure P0 is equal to 1000 hectopascal, the potential temperature of the air parcel is approximately what? That is the question. In the question, a lot of things are given. Many are unnecessary actually. So, yeah, yeah, yeah. So that value is around T and yes, exactly. So only 950 and the initial pressure and temperature is the things that we actually require, and the second values are actually unnecessary. So yeah, so I just wanted to show you this problem as well. Fine. Now we will go back to the presentation. Yeah. So now the next question. So now we are moving on to a different section which basically talks about the sun-earth relationship, the seasons, the solar insolation and all those things. So we have the thermodynamics parts, we have covered the different types of temperature, yeah, different types of temperature, moisture parameters, different stability conditions and all, a lot of things like that. So now we are basically moving on to the sun-earth relationship, different seasons and all those things. So here in this question, higher latitudes receive higher average solar insolation due to attenuation and beam spreading. It is true or false. So in the question, it is telling that the higher latitudes actually receive higher insolation. So is that correct or wrong? Higher latitudes, yeah. Higher latitudes receive very low solar insolation. False is the correct answer. So why this is actually happening? Why the higher latitudes are receiving very slow solar insolation? So there, yeah, yeah. So I am uploading this. I have taken from your study material only. This particular figure, this thing actually I prepared. So whatever I am taking in the class, these presentations are being uploaded in a Google sheet. Actually, you have access to that sheet. Every Yeah, so my presentations are being uploaded there. So you have access to the content. Whatever I'm teaching, you will get the presentations. And these lectures are also being recorded and it is being uploaded in YouTube also. So you can I think every week they are sharing a email asking for this, yeah, asking for feedback. So along with that, this Google Sheet is also being shared. So from that you can access the recorded classes as well as the presentation. Okay. So yeah. So higher latitudes generally receive lower solar insolation. So this is basically due to two reasons. First one is attenuation of the incoming solar radiation, and the second one is beam spreading. So now let's just see what basically means attenuation and beam spreading. So attenuation basically the laws of radiation. So basically, we are losing something due to some um, condition. So that is basically attenuation. So what happens is that, so this is basically our Earth. Then we have a surrounding atmospheric layer. So the outer blue line, so this basically shows you in the atmosphere. So we have atmosphere surrounding the surface of the Earth, right? Now we have solar radiation, which is incident on the top of the atmosphere. So the solar radiation, once reached the top of the atmosphere, it needs to go through, or it needs to pass a particular thickness of the atmosphere before reaching the surface of the Earth. So the thickness of so in the atmosphere there are a lot of particles like dust, cloud, etc. A lot of things are there that are present in the atmosphere. So as this radiation is passing through the atmosphere, it is interacting with a lot of particles. Because of that, most of this, so some energy will be reflected back into the space, some will be absorbed by the atmospheric particles. So different kind of things are happening in the atmosphere. So as it passes through the atmosphere, many of the some amount of solar energy is lost due to reflection, absorption, scattering, etc. So because of this, the amount of solar radiation reaching the atmosphere will be less compared to the amount of solar radiation that is reaching the top of the atmosphere. So at the equator, the thickness of the atmosphere that the solar radiation has to pass before reaching the surface of the Earth is comparatively less compared to the thickness of the atmosphere that the solar radiation has to pass before reaching the surface in the polar region. So as you can see here, if this line A is the incoming solar radiation, so in this case this blue line, or this is the thickness of the atmosphere that the solar radiation is passing through before reaching the surface. Whereas over the polar regions, this is the thickness of the atmosphere that it needs to pass through before reaching the surface. So this distance, or the thickness of the atmosphere that the solar radiation has to encounter before reaching the surface of the Earth is greater than the thickness of the atmosphere the solar radiation has to encounter before reaching the surface of the Earth near the equator. So because of this, the attenuation or the loss of radiation due to the interaction with the atmospheric particles is higher over the poles or the higher latitudes compared to that of the lower latitudes or the equator. So this particular phenomena is known as attenuation. So this is one reason because of which the insolation or the incoming solar radiation over the polar regions or the higher latitude regions is less compared to that of the lower latitude regions. The second reason is known as beam spreading. So what does it basically mean? So beam spreading is the area over which the incoming solar radiation is getting distributed. So over the equator, because of the shorter distance, so this red area is the area over which the incoming solar radiation is getting distributed. This is the area over the equator, whereas over the higher latitudes, because of the higher distance the incoming solar radiation needs to be distributed over a larger area compared to that of the equator. So here this is direct solar radiation, whereas here the solar radiation is traveling more distance and it is basically getting distributed over a larger area over the higher latitude region compared to that of the lower latitude region. So because of this, again, the amount of solar radiation which is reaching, if we look at per unit area how much insolation is reaching in the higher latitudes, this will be less compared to that of the equatorial region. So here per unit area it will be receiving more energy, whereas here per unit area the amount of energy received will be less, because here the area on which the incoming solar radiation is getting distributed is high. So this is the second reason. So due to two different reasons, the higher latitudes actually receive lower solar insolation compared to that of the lower latitudes. First one is attenuation, which means the solar radiation has to travel more distance or need to encounter a larger thickness of the atmosphere before reaching the surface of the Earth. And the second one, because of the longer distance, the beam the incoming solar radiation is being distributed over a larger area in the high latitudes compared to that of the equator. So because of this also the incoming solar radiation is less. So these are the two different things. Now if you look at the how the solar radiation is getting distributed based on the latitudes, you can see the polar regions are actually um, having higher values of solar radiation. Sorry, the equatorial regions are having a higher values of solar radiation, like this Africa, India, and all those are actually having larger. And as we go up in the latitude, you can see it is kind of decreasing. So the green color basically shows you lower solar insolation, and the red values are actually showing higher solar insolation. So because of this, um, the higher latitudes are actually having lower incoming solar radiation compared to that of the equator. I hope it is clear. Now the next question. The angle between yeah, the angle between the plane of ecliptic and the Earth's axis is what? That is the question. So what will be the answer? You know, angle between the plane of ecliptic. Yeah. So yes. 66.5 degrees is the answer. So, what is the plane of ecliptic and the Earth's axis? So we know that the Earth's axis is actually um, not like 90 degree. It is actually a bit tilted, and that axial tilt or the angle of tilt is basically 23 0.45 degree, I guess, approximately 23.45 degree is the axial tilt of our Earth's axis. And now, because of this tilt, so based on the tilt only, we have different latitudes. The different latitudes are also having this tilt. So when we draw an equatorial plane, this will be actually a bit tilted. This will be normal to the axis. The equatorial plane is basically normal to the axis. And now we know the Earth is actually revolving in an elliptical orbit around the Sun. So that elliptical orbit is actually perpendicular to the normal. The Sun doesn't have a tilt. It is like the it is properly like this, aligned like this. So the orbit is also perpendicular to the Sun's axis. So because of this, if we have a plane of ecliptic, which is basically plane of ecliptic is basically an imaginary plane that bisects both the Earth and the Sun. So it is perpendicular to the Sun's axis. So this basically connects the Earth with the center of the Sun on this plane of ecliptic. So that is perpendicular to the um, Sun's axis, which makes 90 degree with the Sun's axis. Now, what is the angle between the plane of elliptic and the Earth's axis? So, Earth's axis is tilted 23.45 degree from the perpendicular. This is the perpendicular to the elliptical orbit. So, it is actually tilted to 23.45 degree. And now we have the plane of elliptic. This is the plane of elliptic. This is making an angle 90 degree with this perpendicular. So because of the axial tilt, if we look at this angle, which is the angle that is made by the plane of elliptic and the Earth's axis, it will basically be 90 minus the axial tilt, which is 23.45 degrees. So this will be 66.5 degrees. Correct? Yeah. So, okay, yeah. So that I told you approximately, I'm not sure. So it will be 23.5. Yeah, sorry. No, it is not there. No. Yeah, at this kind of, it is 23.5 only. I just wrote it by mistake. I guess it's just. This actually kind of change. So we discussed this Milankovitch cycle, right? You were there? we were discussing like natural climate changes. Parameter. Yeah. Okay. So the value is 23.5 degree. This I wrote by mistake. But just so you know, so there is something. So we were discussing. So you know that we were talking about anthropogenic climate change, because, which is basically due to the enhanced anthropogenic emissions, enhanced greenhouse effect, etc., etc. So this is basically caused by humans, right? So now there is something known as natural climate change, which is actually happening naturally. We are not doing anything, but it actually happens as part of the nature. So among the parameters that actually lead to this natural climate change, there is something known as the Milankovitch cycle. So in the Milankovitch cycle, there were three different um, factors which actually keeps on changing. But in that case, the time period or the cycle of the changes are very less, not like, so in case of anthropogenic climate change, in the last 100 or 200 years, we are actually experiencing a temperature change of 1 to 1.5 degrees Celsius. But in the case of Milankovitch cycle, in that case, the changes are actually happening once in 43,000 years, 11,000 years, kind of like that. The time period is very high. But in case of anthropogenic climate change, it is very rapid. So that is the difference. So there is one change which is actually happening. One parameter was that the angle of axial tilt is actually changing from 22.5 degree to 24.5 degree. This keeps on changing, and currently we have a value of 23.5. Please recheck the numbers. I think these numbers are correct. Maybe slight variations will be there. So anyway, like basically the axial tilt changes from 22.5 degree to 24.5 degree. So this change is actually happening, but it is very slow. There won't be any visible change in the climate because of these variations. So currently we are at a stage when we are actually experiencing an axial tilt of 23.5 degree, and this keeps on changing. It is actually moving from 22.5 to 24.5. Yeah. And just check what was the, I forgot what was the time. I think it is once in 23,000 years or something. 23,000 is 23,000 years is the time period at which it actually completes one cycle, which means it will start at 22.5 degree, then it will change to 24.5, and it will again come back to 22.5. Milankovitch cycle. So this is basically another Milankovitch cycle. I'll just check the time period at which it actually happens. Three different parameters were there. One of it is this change in axial tilt, and another change was this happens in 41,000 years actually. It is changing from 22.1 degree to 24.5 degree, 5 degree, 22.1 to 24.5, and this actually happens in a time period of 41,000 years. Yeah, so this is basically known as oblique. Yeah. So this is basically known as obliquity. This change is basically known as that. And there is two different other parameters are also there. You can go back and see it. So yeah, here anyway the value is 66.5 degrees Celsius. The elliptical plane is always perpendicular to the sun's axis, so it is actually making an angle 66.5 degree with the axis of Earth's axis, which is making 23.5 degree with the perpendicular, with the normal. So yeah, next question. Which of the following factors contribute to lower average temperature at high latitudes compared to that of the equator? We just discussed this. What were the two different parameters? So the first one is increased atmospheric attenuation of solar radiation. Second one is greater beam spreading of solar radiation. Third one is higher concentration of greenhouse gases at high latitudes. The Earth being significantly closer to the Sun during high latitude summer, which will be the two reasons because of which we are actually having lower average temperatures. So two factors we already discussed. Yeah, yes, first two only. So these two are the answers. We just, yes. So attenuation and beam spreading. These are the two reasons because of which we have lower solar insolation at the polar regions, and which is basically leading to lower average temperatures compared to that of the equator. Now, what is a black body? A black body is a perfect absorber with emissivity is equal to 0. Is it true or false? False. So black body is a perfect absorber as well as a perfect emitter. So both, the first part is correct, in which it is stating that the black body is a perfect absorber. After absorbing all this radiation that is being incident on the black body, it also emits it. It emits radiation in the whole of the electromagnetic spectrum, which means its emissivity is also 1. Emissivity is 1, not 0. After absorbing, the black body re-emits all the radiation. Re-emits the radiation as well. So because of that, both are actually 1. It absorbs all radiation and also it emits back as well. So because of that, emissivity it will be 1, not 0. And generally we assume in the problems that we do, we assume Earth and Sun as black bodies, which is having an emissivity of 1. So in the Stephen Boltzmann law and all, we basically assume that the emissivity is actually 1 in case of Earth and Sun. Now, the next question. The plane of circle of illumination of the Earth is aligned with Earth's axis. Yeah, yeah, no. In when we in it is not actually absorbing. Yeah, yeah, the emissivity of Earth, right? Okay, I'm not sure what is the value of Earth's emissivity, but generally I'm not sure about the value. I can say it is ranging between 0.5 to 0.99. Yeah, because there will be a lot of attenuation, like the ocean. There is different. Earth is basically having different kind of surfaces. Like so, we have oceans, we have highly reflecting deserts. So it is basically a combination of all these things. So oceans generally absorb all the radiation that is coming, whereas deserts reflect most of the radiation that is incident on. So because we have different types of surfaces and different land cover, it kind of varies. So we just so it generally basically varies from 0.65 to 0.99. Yeah, that is. I think um, yeah. So what is basically being told is less in case of water, vegetation, etc. It basically shows the higher values of 0.95, whereas in case of in yeah, in case of water vegetation, sorry, in case of water and vegetation, it will be having a lower value around 0.65, and in case of highly emitting surfaces like ice and everything, there will be a higher value of 0.95. I think maybe global average will be coming in between these two, 0.65 to zero point 0.9. In between something, in between an average value will be mostly average emissivity. The average of 0.65 and 0.99, like that range average. So yeah, 0.65 plus 0.99 by 2. that will be the average wavelength approximately. But yeah, in problems we yeah uh, yeah. So the next question. Yeah. The plane of circle of illumination of the Earth is aligned with the Earth's axis. So as we were discussing, the Earth's axis is actually a bit tilted, but the elliptical orbit which upon which the Sun is actually rotating is in a perpendicular plane. So because of that, the plane of circle of illumination is not actually aligned with that of the axis of the Earth, but that is actually perpendicular to that elliptical plane that we discussed earlier. So because of that, it won't be aligned. So the answer will be yeah. So it will be false. So as you can see in the figure, this is a circle of illumination. So you can see like this region is basically having night, whereas the brighter side is actually having daytime. So circle of illumination is basically, I'll just tell you what the circle of illumination. So circle of illumination is basically the imaginary boundary on the Earth's surface that separates the half of the planet experiencing daylight from the other half. So that's the circle of illumination. Now the next question. On an equinox example during March 21 or September 22, approximately how many hours of daylight does a location on the equator receive? So I hope you know different. So as the Earth is moving, as the Earth is revolving around this, yeah, the answer is 12 hours. So we know that the Earth is revolving in an elliptical orbit around the Sun. So as it is moving because of the axial tilt and all, we have this circle of illumination keeps on changing. So during equinox, both the northern and southern hemisphere will be receiving equal amount of solar radiation. So because of this, we generally have equal days and equal nights. So over the equator, this will be exactly 12 hours. Equator, the amount of radiation reaching will be both equally distributed during the day and night. So it will be 12 hours. And when it comes to as it revolves, and when it comes to a summer solstice, during which the northern hemisphere will experience summer and the southern hemisphere will experience winter, the northern hemisphere will be having longer days and shorter nights, whereas the southern hemisphere will be having longer nights and shorter days. And again, there will be equinox where it will become equal, and again when the winter comes, the axial tilt of the earth is actually facing away from the sun. So in that case, the northern hemisphere will be experiencing winter and the southern hemisphere will be experiencing summer. So here in this case, the northern hemisphere will be having longer nights and shorter days, whereas the southern hemisphere will be having longer days and shorter nights. So during equinox it will be so 12 hours. This is again the next question. During the June solstice, approximately how many hours of daylight does a location at 70-degree latitude experience? So 70-degree latitude will basically come in the polar regions. 70-degree north, yeah, it's very close to the polar regions, or it basically comes in the polar regions. And June, yeah, and June is the period when the northern hemisphere basically is having summer solstice. So because of which it is always illuminated to the sun. even this Earth rotates, that region will always be experiencing sunlight. So because of that, it will be 24 hours. Whereas, what will be the condition in the 70 degrees south during June solstice? How it will be? Yeah, yeah, it will be 24 hours night. 70 degrees south, it will be 24 hours. On an equinox, all locations on Earth receive approximately 12 hours of daylight. Is that correct? During equinox, all, yeah, approximately it receives equal amount of like 12 hours of daylight, 12 hours of daylight and 12 hours of night. So it is approximately true. The average solar radiation at the top of the atmosphere would be dash if the radius of the Earth were doubled and the solar constant remained the same. So we have discussed this solar constant and solar emission and everything earlier. So if, just to revise, we will just solar constant is basically the amount of radiation that is reaching at the top of the atmosphere per unit area. The amount of solar radiation that is being reaching is reaching at the top of the atmosphere per unit area. So we started from the energy emitted by the sun. So first we need to find the energy. How much energy is being emitted by the sun? So as we told earlier, we are assuming that Earth and Sun are black bodies. So in that case, according to Stephen Boltzmann law, what will be the energy emitted by the Sun? You remember the law? What was Stephen Boltzmann law? The energy emitted by a black body is given by, yeah. So E is equal to sigma T raised to 4, where sigma is Stephen Boltzmann constant and T is the temperature of the Sun. So let's assume the temperature of the Sun is approximately 6000 Kelvin. And sigma is basically 5.67 into 10 raised to minus 8. I forgot the units. I think it will be Kelvin raised to minus 4. Yeah. Huh. Sorry. It will be Kelvin raised to minus 4 watt meter raised or Joule Kelvin raised to minus 4 also. Both are correct. From the equation, if you just do the dimensions. So yeah. Yeah, so that is the value of sigma. So from this you can find the energy emitted by the sun per unit area. What will be the value? Energy emitted by the sun will be, how much it will be? 5.67 into 10 raised to minus 8 into 6000 Kelvin. How much you are getting? I'm getting a value of around 7.34 into 10 raised to 7 watt per meter square. This is the energy emitted by sun per unit area. Now if you want to find the total energy emitted by the sun, yeah, okay. So how can you find the total energy that is being emitted by the sun? Can you tell me? You can multiply it by the, yeah, into, so this is, yes, exactly. So this can be multiplied, the surface area of the sun. 4 into 3.14 into r. R is given in the figure. So this is the radius of the sun, which is 6.96 into 10 raised to 5 kilometer. You have to convert it into meter. So the total energy emitted by the sun will be 7.34 into 10 raised to 7 into 4 into 3.14 into r, which is 6.96 into 10 raised to 5 or 10 raised to 8 the whole square. So how much will be the total energy that is being emitted by the sun? Yeah, I think I just lost the connection. Six point 64 into 14 joule. I'm getting actually 4.46 into 10 raised to 26. What I'm getting a value of 4.46 into 10 raised to 26. Can you check again actually? Yeah, I'm doing wrong. I will also check once more. Just let me know which one is correct. Okay, okay, fine. Then it's R squared. So the value will be 4.46 into 10 raised to 25 watt. This is the total energy being emitted by the sun. So now, what is that? So this is being emitted like this, right? So this sun's rays has to travel a distance of 1.5 into 10 raised to 8 kilometer to reach the earth. So this is basically the earth sun distance. travels this much distance, some energy will be lost. So in that case, what will be the energy that is reaching at the top of the atmosphere? Energy received after traveling this much distance. Energy received at the top of the atmosphere per unit area. So in order to find that, let's assume the distance as a sphere, another sphere. So this is being emitted towards all directions. So let's assume this is another sphere which is having a area of 4 pi d square, where d is the distance between the earth and the sun. So it will be, since this is being emitted to the all directions, we have to divide it by the total area, which is 4 pi into distance between sun and earth. So the energy emitted by the sun, yeah. So now we are considering what is reaching the top of the atmosphere or surface of the earth. Sorry. No, radius of the earth wide. So we are okay. Oh, so you are telling like the distance is being calculated from the center of the sun to center of the earth, right? Okay. Since the value is very small compared to that of the total distance, I think we are ignoring that. And it doesn't actually mean from the center we are measuring. No, it doesn't actually mean we are measuring from the center. Um, it doesn't make sense if we are measuring from the center of the earth, right? I think in the figure it just shows like that, but it's just the distance between the sun and earth from the um, how do I explain? It doesn't mean like we are. No, no. The thing is, it doesn't make sense if we are actually measuring from the center of the earth, right? So it's basically from, I think that, what you say? Yeah, that, I think the radius of the earth is around 6,400. Uh, what is the radius of the earth? Probably 64,000 kilometers or something, right? It is given, right? Yeah. The value is around 6.35 into 10 raised to 3 kilometer. So it is not very less compared to the distance of the earth. This matters, right? 1.5 into 10 raised to 8 and 6.35 into 10 raised to 3. So if we measure from here to here, then it's 1.5 into 10 raised to 8 kilometer, right? Yeah. I think because of the shape we are having this confusion. Since it's a spherical shape, the distance is not equal, like the distance to the equator and the distance to the poles are different. So here we are considering the distance to the equator. I hope that makes sense, right? Yeah. So divided by 4 pi d square. So 4.46 into 10 raised to 26 divided by 4 into 3.14 into distance, which is 1.5 into 10 raised to 8. Again, it is in kilometer. So 8 plus 3, 11. It will be 1.5 into 10 raised to 11 meter. what will be the value? Yeah, sorry, it will be this part. Yeah, it is coming around 1570. So the actual value is solar constant value is actually 1360. I think some assumption we made. Maybe I think this value, the temperature of the sun is the exact value is around 5772 Kelvin. We assumed it to be 6000 Kelvin. Maybe because of that, this difference came actually. So the actual value is 5772 Kelvin. So generally, the value of solar constant is 1360 watt per meter. So I think because of this assumption, we have gotten a larger value. Theoretically, we generally take the value as 1360 watt per meter square. So maybe you can redo the calculation with the sun's temperature as 5772 Kelvin rather than 6000 Kelvin. I think that has made the difference. So theoretically, the value of solar constant is generally taken as 1360 watt per meter square. So yeah, so that is the energy received at the top of the atmosphere per unit area. Now again, once this solar radiation reaches the top of the atmosphere, it is actually encountering. So this is actually being emitted to all directions, as I said earlier. So this radiation is actually only illuminating one part of the Earth, right? So only one side of the Earth is actually being faced to the sun. So this is actually being encountered by an area of pi r square, which is the disk that is being illuminated from the surface of the Earth. So solar constant into pi r e square is the total amount of solar radiation that is reaching the top of the atmosphere. And this radiation, whatever we are getting, is basically being distributed over the whole Earth's surface. So we have to, so in order to find what is the total energy received, total amount of solar radiation that is being received by per unit area over the surface of the Earth, we again have to divide it by 4 pi Re square. So this basically gives you the value uh, that is actually given in the question, which is the average solar radiation at the top of the atmosphere. So this is the average solar radiation that is being received at the top of the atmosphere. Solar constant into pi r e square divided by 4 pi r e square. So this is what is reaching per unit area. This is actually illuminating a disk which is having an area of pi Re square. This is only this much region is being encountered by the solar radiation, and whatever radiation is actually reaching this area is being distributed to the whole Earth sphere, which is having an area of 4 pi Re square. So this is the solar radiation that is actually reaching the top of the atmosphere per unit area. Now the question is, what happens to the average solar radiation at the top of the atmosphere if the radius of the Earth were doubled and the solar constant remains the same? So in the calculation of solar constant is whatever is reaching the top of the atmosphere. It doesn't matter what is the radius of the Earth. So after that, we are multiplying it with pi Re square and dividing it by 4 pi Re square to get what is the energy that is reaching per unit area at the top of the atmosphere. So it will be 1360. In the question they are telling like we are doubling the Earth's radius. So it will be pi into 2 Re square divided by 4 pi into 2 Re the whole square. Right? Re will be new Re dash will be 2 Re. That's what they are telling. So what will be the value? Yeah, yeah, exactly. So it will be S by 4. Yeah, it will be 340 watt per meter square. So it doesn't matter if we are doubling the size of the Earth or not. It will always remain the same. It doesn't matter. The radius of the Earth is not influencing the amount of solar radiation that is actually reaching the top of the atmosphere. So that's what it basically means. So the answer will be 340 watt per meter square. So now, let's so now we know the average solar energy that is incident on the top of the atmosphere per unit area of the Earth's surface is given by I incident is equal to S by 4. Right? So part of this incident radius, so this much energy is actually reaching the top of the atmosphere. Suppose this is the atmospheric layer. So this much radiation is actually reaching the top of the atmosphere. So after reaching the top of the atmosphere, part of this incident radiation is actually being reflected back as it travels through the atmosphere. So some part of it is being reflected back due to clouds or aerosols and from the Earth's surface. So as it reaches the surface of the Earth after traversing the atmosphere, some of this amount of radiation is being reflected back by clouds, aerosols, and by some land cover regions as well, some part of Earth's surface. So the fraction of incident radiation that is reflected back is known as Earth's albedo. Fraction of incident radiation that is reflected back is albedo. So in case of Earth, the average albedo is basically having a value of 0.3. The rest of the incident radiance. So what after reflecting, so this much is coming out of the 0.3 percentage is getting reflected back, and what is actually being absorbed by the Earth surface. I absorbed will be S by 4 into, if 0.3 is reflected back, what will be absorbed? 1 minus alpha. So this much is being absorbed by the surface of the Earth. I absorbed or energy absorbed, that is the E. E absorbed as S by 4 into 1 minus alpha. And in case of 0.29, 0.3, 0.29 approximately is the value. Just one more thing. So can you tell me like which is having, what is the albedo value in case of ice? Ice or glaciers, what is the albedo value? Can you tell me? So different surfaces have different albedo values. Yeah. Yes, exactly. So in case of ice, the albedo will be 1, which means all the radiation that is being incident on us is actually reflected back. And in case of ocean surfaces or water surfaces, albedo is very, yeah, approximately close to 0 or very less. Not exactly 0, approximately close to 0. So we have different kind of surfaces. Yeah. So average alpha value is taken to be 0.29. Now, so this is the amount of energy that is being absorbed by the Earth. So Earth will emit heat radiation back to space, assuming the Earth to be a black body. So the heat radiation, the energy that is being emitted by Earth is given by, again according to Stephen Boltzmann law, what will be the energy emitted by a black body? Stephen Boltzmann law, yeah, yeah. Sigma temperature of the Earth, the whole raised to 4. So this will be the energy emitted by the planet or by Earth, where TE is known as the emission temperature. Okay. So generally, if the radiation is actually balanced between each other, E absorbed should be equal to E emitted. This is an ideal condition. So, it should be equal. So in that case, we can write 1 minus alpha into S by 4 is equal to sigma T e raised to 4. In this case, we are assuming that whatever radiation is coming from the sun is being emitted back to the atmosphere. No attenuation is happening within the atmosphere, or there is no heat that is trapped in the surface of the earth or in the atmosphere. In that case, if this was happening, what will be the temperature of the earth? I think we have done this exercise before, but let's just redo it again. So 1 minus alpha into S by 4 is equal to sigma e raised to 4. So it will be 1 minus 0.29 into S is having a value of 1360 by 4 is equal to sigma, which is 5.67 into 10 raised to minus 8 into temperature of the earth. We need to find temperature of the earth. So TE will be 1 minus 0.29. What will be the value? Okay. So the temperature of the earth, as we are assuming all the energy that is being absorbed is being reflected, is being emitted back to the space, temperature of the earth would have been 255.4 Kelvin or approximately minus 18 degrees Celsius. This would have been the average temperature of the earth. But this is not what we generally experience. So what additional thing is actually happening in the atmosphere? Can you tell me? what is absorbing what is actually helping in trapping the heat and maintaining. Yeah, and what exactly? Yeah, which gases are actually leading to this? Can you tell me what is this phenomenon? Yeah, so it's basically greenhouse gases. Yeah, greenhouse gases are actually helping to trap this radiation, and this is what is known as greenhouse effect. So greenhouse effect is actually leading to warmer temperatures and a habitable temperature in the surface of the earth. So what happens is that if the greenhouse effect, enhanced greenhouse effect is actually leading to global warming. So greenhouse effect is actually good, but when it is actually enhancing, it is trapping more amount of radiation and then leading to global warming. So greenhouse gas effect is actually required for sustaining life on Earth. So now what we are experiencing is an enhanced greenhouse gas effect. So now how the greenhouse gas effects work, how it is maintaining the temperature. Let's just see how the greenhouse effect works. So as you told, what the greenhouse gases, mainly water vapor and carbon dioxide, are actually absorbing some of the radiation that is being emitted by the surface of the Earth and is maintaining a higher temperature on the surface. So assume that Earth is, so let's see what will be the temperature once we include the greenhouse gas effect as well. Assume that the Earth is covered with a single uniform layer, single uniform layer of atmosphere that is at a constant temperature, temperature TA. So suppose this is the surface of the Earth. This is Earth's surface, and we are assuming there is another layer on top of this. This is the atmospheric layer. So we have the incoming solar radiation, which is I incident, which is given by S0 by 4 into 1 minus F. This is the incident solar radiation. And then once it reaches the surface, the Earth starts re-emitting radiation, which is given by sigma Ts raised to 4. So let's see, Ts be the surface temperature of the Earth. Based on the surface temperature of the Earth, it starts re-emitting the radiation. So what happens is that all this radiation, instead of going back to the space, some is getting attenuated in the atmosphere. So let's consider. So as it passes through the atmosphere is absorbing some amount of this energy and it starts re-emitting radiation again. So the energy that is being re-emitted by the atmosphere is given by sigma Ta raised to 4, and it re-emits on both directions, not only upward but it re-emits in the downward direction also. So the atmosphere, after absorbing some of the radiation that is being emitted by the Earth's surface, it re-emits some amount back to the space and some amount back to the Earth's surface as well. Yeah, yeah. It's the surface land surface temperature. Land surface temperature. So it will be an averaged value. Since we are not considering like different, it will be heterogeneous, so it will be a globally averaged value. It will have variations over different surfaces, but here we are considering an average value. Yeah. So, yeah, sigma Ts raised to 4 will be the energy being emitted by the surface. The atmosphere will absorb this energy and it will start re-emitting on both sides. Some back to the space and some back to the Earth's surface. So now if we look at the energy balance at the surface of the Earth, energy balance at the Earth's surface. At the Earth's surface, what is the incoming radiation? We have incoming solar radiation, which is S0 by 4 into 1 minus alpha. and we have some additional radiation that is being re-emitted by the atmosphere, which is sigma Ta raised to 4. That is also coming back to the surface, right? Sigma Ta raised to 4. This will be equal to the energy that is being emitted by the surface, which is sigma Ts raised to 4. I'll write it here. So at the Earth's surface, incoming is 2. One is solar radiation, which is S0 by 4 into 1 minus alpha, plus the energy that is being re-emitted by the Earth's atmosphere, which is sigma Ta raised to 4. This will be equal to sigma Ts raised to 4. Now the energy balance at the, so this is at the surface. Now we look at the energy balance at the atmosphere. At the atmosphere, if we look at what is the, at the atmosphere, no, the whole atmospheric column. Yeah, top of the atmosphere we will write. Now, if we are considering the atmosphere, the energy that the atmosphere is receiving is what is actually being emitted by the surface. So the energy the energy received is sigma Ts raised to 4, and the energy is re-emitted as sigma Ta raised to 4 plus sigma Ta raised to 4, which is both directions, upward and downward. So 2 sigma Ta raised to 4. So sigma Ts raised to 4 is equal to 2 sigma Ta raised to 4. This is the energy balance at the atmosphere. Now as you said, let's see what is the energy balance at the top of the atmosphere. At the top of the atmosphere, the energy that it receives is S0 by 4 into 1 minus alpha, right? This one, and what it re-emits is this one, sigma T raised to 4. Yeah, yeah. So S0 by 4 into 1 minus alpha is equal to sigma T raised to 4. This is at the top of the atmosphere. Now we have 3 different equations. Now from this equation, so earlier when we discussed about the sigma emissivity temperature, or the energy that is being emitted by the surface, emitted by the earth, this emission is actually happening from the top of the atmosphere. From the surface, it is actually interacting with the atmosphere, then it is being re-emitted from the top of the atmosphere. So this Ta is basically equal to the T emissivity, or the energy that is being emitted from the atmosphere. So Ta is equal to Te. That is one thing. And the second one is Ts, which is the surface temperature of the earth. From this equation, we can write it as sigma and sigma will go. It will be 2 raised to 1 by 4 into T A raised to 4. So the relation between the surface temperature and the atmospheric temperature is Ts is equal to 2 raised to 1 by 4 into Ta raised to 4, or Te. Ts is equal to 2 raised to 1 by 4 into Te, since this both are equal. And we know what is the value of Te, right? Earlier we found out what is the value of Te. Now from that, can we find the value of Ts? Yes, exactly. So the surface temperature will be 0.25 into 255 Kelvin that we got earlier. So the surface temperature will be around 303 Kelvin, or it is actually 30 degrees Celsius. So this is the average surface temperature of the earth that we actually see. So because of the greenhouse gas, we are actually having a temperature of 30 degrees Celsius. I hope it is clear. Now when we included the greenhouse gas effect also, we are getting a surface temperature of around 30 degrees Celsius. Now let's solve this question. So if the atmosphere absorbs 100% of the thermal radiation, the surface temperature Ts is equal to 2 raised to 1 by 4 into Te. Is that correct? True or false? So here actually we assumed that, sorry, Yeah, F is equal to 1 is given. No, here we are considering it is absorbing all the radiation, right? Then it is true, correct? So here we assume that whatever energy that is being emitted by the surface, which is sigma Ts raised to 4, is being absorbed by the atmosphere, right? And then it is re-emitting it. That's what we assume here. Which means the atmosphere is absorbing all the radiation. And from this assumption only we got the relation that Ts is equal to 2 raised to 1 by 4 into T. That's what we saw just now. So this is actually true. Ts is equal to 2 raised to 1 by 4 into T. Yeah. So the answer is true. Now the second question. If the outgoing long wave radiation is 240 watt per meter square and the solar constant is 1360 watt per meter square, Earth's albedo assuming energy balance. So outgoing long wave radiation is given as 240 watt per meter square and solar radiation, incoming solar radiation or insolation is 1360 watt per meter square. So assuming Earth's energy balance. Yeah. So if the so we essentially assume S by 4 into 1 minus alpha is equal to I emitted. I emitted, right? Like what are being emitted is both are equal. This is absorbed and this is what is being emitted. These both are equal. That's what we generally assume. So 1360 by 4 into 1 minus alpha is equal to 240 watt per meter square. That's what being given in the question. S is 1360 and outgoing long wave radiation is given as 240. So in this case, what will be the value of alpha? So 1 by alpha will be 240 into 4 divided by 1360, which implies alpha will be, what will be the value of alpha? Yeah. Can you tell me what will be the value of alpha? Hmm. Yeah. So it will be 0.29. Yeah, this we already discussed. The lowest albedo is found over oceans in subtropical regions due to low cloud cover and dark ocean surface. So we know that the lowest albedo is actually over the oceans. Yeah. So why oceans are actually having a lower albedo? Because ocean surfaces are very dark. And over the subtropical regions, if you remember, we discussed different atmospheric cycles like Hadley cell, Ferrel cell, and polar cell. So in that, we were seeing that over the subtropical regions, this sinking of air parcels was happening, which will basically lead to low cloud cover over the region. Low cloud cover, in the sense, more radiation will be incoming. So because of that, oceans generally have very lower albedo, and where the incoming solar radiation is also high, the absorption will be high. So that's why subtropical region, oceans or the subtropical regions will be having lowest albedo compared to all other ocean surfaces. So this is actually true. Now, which of the following would happen if Earth had no atmosphere? So the first one, emission of the temperature of the Earth will be equal to surface temperature of the Earth. Emission temperature of the Earth will be equal to surface temperature, greater than surface temperature of the Earth. Emission temperature of the Earth will be less than surface temperature of the Earth. Surface temperature of the Earth would be warmer. So they are telling three conditions they are giving. Yeah. If there was no atmosphere, Ts will be equal to Te. Once you consider the greenhouse gases, we know Ts is actually 2 raised to 1 by 4 into 3. So when you consider greenhouse gas emission, this will be the surface temperature. So the first one. If there was no atmosphere, then the emission temperature and the surface temperature will be. The Earth's surface is in radiative equilibrium. The total incoming solar radiation incident upon the surface is 300 watt per meter square. So let this be the surface. Then we have a thin layer of atmosphere above it. Then the question it is given, the surface is in radiative equilibrium. The total incoming solar radiation which is incident upon the surface is 300 watt per meter square. This is the total incoming solar radiation that is incident on the surface, and the surface also receives 150 watt per meter square. So some amount will be re-emitted by the Earth's surface. This will be absorbed by the atmosphere and it will re-emit in both directions, right? So and it is given the surface also receives 150 watt per meter square of downward long-wave radiation from the atmosphere. So atmosphere is actually absorbing and re-emitting around 150 watt per meter square back to the surface of the Earth. The outgoing long wave radiation emitted by the surface is 450 watt per meter square. This is 450. Based on the energy balance at the surface, what will be the value of surface albedo? At the surface, the energy balance will be incoming. What all are incoming? This one is incoming. This is the incoming solar radiation plus the energy that is being re-emitted by the surface, re-emitted by the atmosphere. So 300 plus 150 is equal to the energy that is being re-emitted from the surface is around 450. Yeah, 300 into 1 minus that. Yes. It will be 300 into 1 minus alpha. So, what will be the value of alpha? It will be 300 into 1 minus alpha is equal to 450 minus 150, which will be 0, which means alpha is equal to, yeah, the value of alpha will be 0 is the correct answer. Now, according to the simplified models, what is the primary effect of increasing greenhouse gases? What is the effect of increasing greenhouse gases? If we increase the greenhouse gas, what will happen? Decreasing the Earth's albedo, increasing the solar irradiance, increasing the fraction of thermal radiation absorbed by the atmosphere, decrease the emissivity of the Earth's surface. Which will be the correct answer? So Earth's albedo just depends on the land use, land cover of the Earth. It doesn't matter if more greenhouse is present or not. It is basically a characteristic of Earth's surface. So decreasing the Earth's albedo is wrong. And increasing the solar radiation. We calculated the value of 1360 watt per meter square, which is the amount of radiation which is reaching the top of the atmosphere per unit area. This has nothing to do with, so this is before entering the Earth's atmosphere, right? So what is coming from the sun is not influenced by the amount of greenhouse gases that is present in the atmosphere. So this is also wrong. And the third one, increasing the fraction of thermal radiation absorbed by the atmosphere. As you know, we are, yeah, so this is the correct one. And again, the fourth one, decreasing the emissivity of the Earth's surface. So this also is a characteristic of Earth's surface. What exactly is present? It has nothing to do with the atmosphere. The emissivity is a characteristic of the surface itself. It doesn't matter. It does the Earth's atmospheric concentration doesn't influence the Earth's emissivity. So that is also false. This is also false. So the third one is the correct. Yeah, I think we will stop here. That's all for today. Yeah, so that was the last question. Yeah, thank you for attending. If you have any doubt, you can ask or we will stop. Okay, so next, yeah, next class I'll explain that. So let's see how is it. I think it's better to discuss assignment questions. Like, do I need to explain the assignment question from the current NPTEL course, or should we try to solve different questions? I think these questions here already different questions will be better, right? Yeah. Then I think, yeah. Then from next class, we will try to solve different questions. So if you have any doubt in the assignment question that is actually being given in the NPTEL class, you can just ask me. We will try to do that. Otherwise, we will try to solve different questions. Okay. Yeah, I get that. I think, yeah, that will be better. We'll do that. From next class, we'll do that. Oh, yeah. Yeah, next class, we will. Yeah. Next class, we will discuss that. Okay, then. Yeah. Bye. Thank you.